In this last video for Lab 2, so here we are in Lab 2, I'm on page 5. I'm going to go through example 3, and I haven't said it explicitly, but in case anyone's confused, the way the labs are set up here is there's always an R script indicated here. There's an R script associated with the example, and then there's often a data set associated with the example as well. So the .r is the R script and the CSV would be the data set. And what I'm doing in the lab handout is walking through the lines of code that are in the scripts and sort of explaining those to you. So I'm going to walk through this example here, and the way we start off is I want to import this barley extract data set that we've been looking at sort of continuously as we talk about distributions and power. So if we go into Lab 2, this would be Lab 2 example 3, the CSV file. I'm going to give it extract.dat as the name for it, because that's what I refer to it as in the provided script. And I'm going to bring that in, and it all looks good. So these are the 14 observations, extract observations, and we have two variables, sample ID and extract. If you were to walk through this, you would also go and open the file containing the script associated with this example, and that would be lab2 example3.r, and bring up that particular file. And what you'll see here is that I've written out all the code along with these lines that start with the hashes. These are my commentary and annotations. And what this script is going to do is going to perform a Shapiro-Wilk test on the data. It's going to perform a t-test with a specified null hypothesis and also a power test. So that's what's happening in the script. So you can go through and open up the data and run through that. What I want to do here, I'm going to start a new script. Actually, I'll leave that here for now. What I want to do here is come over to the management window here. We haven't really used the help tab yet, and I want to do that now. If you go to the help tab, there's this search field right here, and you can type in t-test. There's the t-test function, and as for, and you get a whole bunch of results in R. And if you scan down through here, you'll see that in the base stats package there is the student's t-test, and if you click on that, you get a whole manual about how to use this particular test. And the way these help pages are set up, it gives you the name of the function at the top, a quick description, and then it gives you usage. And usually what it'll give you is this kind of example that has all the parameters laid out for it you could potentially specify, and then following that are some definitions of the arguments. And this is exactly what I've pulled into your lab handout. So when you go into the help menu and ask for t-test, what you see is this, is that you have to specify the data set that you're interested in. And if you're comparing two samples to one another, you would have two data sets, X and Y. You have to specify what the alternative hypothesis is going to be, and this basically comes down to either a one-sided or two-sided test. You can specify the null hypothesis, that there is no difference, or that the mean of the population is 0, or that there's no difference. You can specify whether the values are paired or unpaired, and whether or not their variances are equal, and what your specified confidence level is. Now, if we wanted to run a very quick t-test, sort of a one-sample, two-tailed t-test on this barley extract data, that's exactly what we have in this script right here. I'll space these lines out so you can see it. We're going to run a t-test here on the extract.dat data set, but not the whole data frame, just the extract column, just the 14 numbers. And here I'm going to specify a null hypothesis of 78. In other words, I'm asking whether or not this particular sample came from a population with a likely true population mean of 78. If I send that to the console, it runs the one sample t-test very, very quickly. It calculates the t value. We have the correct degrees of freedom, 13, it's 14 minus 1, and it's giving me a p-value, which is much, much lower than our type 1 error rate of 5%. And so we would conclude that the true mean is really not equal to 78. The mean of this particular sample is basically 76, 75.9. And this is the example we went over in lecture, where we built a 95% confidence interval about that mean. That confidence interval spans 75.2 up to 76.6. Clearly, this 95% confidence interval does not include 78, and so that's another way of interpreting why we would reject the null hypothesis, and we would conclude with 95% confidence that this sample came from a population whose true mean is not equal to 78. So that's running the t-test. The next thing we can do is ask, well, what was the power of that test? What was our type 2 error rate in this particular case? Did we have sufficient replication to be able to reject the null hypothesis when in fact it was false? And now you can imagine, or you would guess, because we have such a low p-value, we clearly had the power to detect a false null hypothesis. So when we ask about the power of this test, we expect that power to be quite high. The way we ask about the power of a test is you could go over to the help menu again. Let me open up this window. I could ask power t-test. And here in the stats package, we can perform power calculations for 1 and 2 sample t-tests. And we get a very similar help page that we had for the regular t-test. And that's what I've pulled into page 5 of your lab handout. This is the structure of this particular function. When you want to ask what the power of a t-test is, remember that power is uniquely constrained once the sample size is set, your detection difference is set, that's delta, you know the variance, or the standard deviation, and you've specified your type 1 error rate. If these things are all specified, power is set. So if you want to apply this power t-test in a specific case, you have to fill in all of these arguments. Now clearly, the number of samples I can get by just asking what the length is of the extract column in my data set. That's going to give me the number 14. My detection difference, if I have a null hypothesis of 78, the detection difference is just the difference between that null hypothesis and the mean of my sample. Similarly, I can specify the standard deviation of my sample by applying the standard deviation function to the extract values in my data set. I can set my significance level. This is my type 1 error rate of 5%. It's a 1 sample test, and it's a 2-sided test. If you specify all that, and that's what's happening in the script here, open this back up. This line 15 here, power t-test, I've gone through and just populated all those arguments based on my sample, and when I send that to the console, it's interpreting things correctly. It's taking the delta that we have, and remember that delta is going to be the difference between 75.9 and my null hypothesis of 78, so it's just a little bit over 2, what I would expect. This is the standard deviation of my sample. This is the amount of noise I have in my sample. I've specified a type 1 error rate, and not surprisingly, I have a power that's very, very close to 1. And the reason I have that power is because my distance is nearly twice as big as my standard deviation. In other words, I'm not really asking a question that requires a lot of precision. Now I could, if you remember back in the lecture notes, page 5 from lectures 3 and 4, let's bring our null hypothesis down a little bit. Let's bring it down to 74.88. This was an example on page 5. In which we use the power formulas to manually calculate the power of this particular question. And what this is asking is, do we have sufficient replication to conclude with the level of confidence that we want, our type 1 error rate, that our sample came from a population or did not come from a population with true mean of 74.88. Now just up front, you can see the 74.88 is much closer to 75.9 than the other null hypothesis was. If we ask this question, you'll see that everything else stays the same. We still have the same standard deviation, the same n. What has changed is that our detection difference has dropped from 2.057 to 1.062. Now it's much more similar in magnitude to the standard deviation of my sample, and you'll see that our power dropped to 85%. And this is exactly the result that we got when we did this calculation by hand in lecture. Now, the t-test clearly can be used for more situations than just calculating or hypothesis testing for single samples. If you scroll down your lab handout, you can run a t-test for 2 independent samples without assuming equal variances between them. And it's what I've given you is just a dummy data set. Here's sample of height 1, here's samples of height 2, and what I want to know is it likely that these 2 samples came from the same population or not? And in this particular case, what you see is that we have a very high p-value. In other words, we really don't have sufficient evidence to reject the null hypothesis. And the 95% confidence interval around the difference of their means spans 0. And what that means is that we cannot conclude that the difference in means of the populations these came from are any different from one another. Now this is the default of the t-test function, is not to assume equal variances. This is the Welch 2-sample t-test. You can also have run a t-test for 2 independent samples assuming equal variances, and in that particular case you got to do a little bit more work. In the t-test function you would specify that variances are equals true, and then you actually have to calculate what that pooled variance is, and you can see here I've just taken the average of the variances of the 2 samples to give me a pooled variance. The power t-test function looks very similar. The only thing that's different here is that we have a 2-sample t-test like we had up above. This was also a 2-sample t-test. And what you'll see is that the p-value actually doesn't change that much. We got 0.5847 here. Assuming, not assuming equal variance, we had 0.5869. What this is telling you is that we actually don't have, the 2 samples really don't differ that much from one another in terms of their variances. And so this is a case in which assuming equal variances seems to be a justified thing to do. If you go down in the lab handout, we also have t-tests for paired samples, and it goes through that example as well. So take a look at all of this. The functions themselves, once you get a hang of the function and the kind of arguments that they require, it's quite easy to program. But it's good to spend a little bit of time looking over this output and making sure that it's all making sense to you.